So our duration idea focuses around understanding our price based on our interest rate. So we need this P of I formula as often as we can get it. Let's start with a zero coupon bond. And I'm going to make my life easier. We'll use the future value of 1. If I've got a future value of 1 for a zero coupon bond, we're going to have an N-year term. And that means we'll have a spot rate, Rn. Let's call that I. What's my present value? This is a single payment of 1 to be made in N years. What's its value today? Regular ordinary compound interest.
1 plus
Our,
I,
okay,
then for negative n times 1.
times 1. Or if you'd rather v to the n, either way. This is our formula P of I. 1 plus I to the minus n. We did this in our example on Tuesday with that one payment that was going to be due in 10 years. And we figured out that the duration was n. So I'm hoping that the duration is n here. So let's make a check. What is the formula for the Macaulay duration at this interest rate? Okay, that's the sum of n times the payment times the interest rate. So it's n 1 plus I to the minus n times 1 divided by the payment without the time, 1 plus I to the minus n. Oh, that is exactly n, just what I wanted. And that matches with what we came up with Tuesday, that the duration, the Macaulay duration of a single payment is the term of that payment. And then the modified payment, sorry, the modified duration is going to be the derivative of pi with respect to t divided by pi. There's a minus sign in here, there. So let's work that out. This is di, not dt. I wrote dt, it's di. It's the change with respect to the interest rate moving. So I go back up here. What's the derivative of this expression with respect to I? Look, there is some calculus. What do I do with this n? I'm taking my derivative with respect to I. So my variable's on the inside, so it's stuff to a power. Okay, power rule time. Minus n, 1 plus I to the minus n minus 1 times the derivative of the inside. Chain rule. But I'm taking my derivative in I. The derivative of 1 is a constant. The derivative of I is just 1. So the chain rule gives me a 1. Oh, the two negatives cancel. So I have an n on top. And then what happens here? What am I left with? Aha. 1 plus I to the minus 1, or n over 1 plus I. That is exactly the Macaulay duration divided by 1 plus I, which is what I was hoping to see. Whew. All right. So with a zero coupon bond, the Macaulay duration is the term of the bond, and the modified duration divides by 1 plus I exactly the way we wanted it to. What about coupon bonds? Let me go back to our idea of the Macaulay and the modified durations. Coupon payments are small by comparison to the redemption value, so I would expect that a weighted average would be larger when we have a large redemption value. Duration should be increasing as the coupon rate. Should duration be increasing as the coupon rate goes up, or should it be increasing as the coupon rate goes down? Where should my relationship be between the coupon rate and the duration? I need to fill in that blank. Want to think of this as a weighted average. The redemption value is big and it's on the far end. The coupons are small and they're scattered around on the left end. But they go all the way up, right? Small payment, small payment, small payment from time 0 all the way to time n. But then there's that giant payment for the redemption value. If I want the duration to get bigger, do I need to make the coupons bigger or smaller? Smaller. So that means as my coupon rate decreases, the duration increases. And vice versa. So if I have an increase in coupon rate, I should expect the net duration to decrease because the weighted average will come closer to time 0, further away from redemption. This also goes with the idea of having more or fewer coupons. If I have more coupons, I'll have more weight further down. But it'll also spread up in towards the redemption value as well. I would expect the duration to decrease, but it doesn't always.
When you see
More frequent coupons. So if I had annual coupons versus semi-annual coupons versus potentially quarterly coupons. Because if I have more of them at the same nominal rate, then I would be making more payments further down, and I should expect a decrease in my duration most of the time. But if I have the same effective rate, then those coupons will all be smaller. So my duration might increase. So it's now going to depend on whether you talk about the same nominal rate or the same effective rate. It always is. Okay. There's an example in the text. The example in the text is not at all obvious. They ask for an arbitrary face value. Piece of paper. For an arbitrary face value, a coupon rate of R per year with N coupons until maturity and a yield of J per year. I want to find the duration. Now, here's the actual statement in the book. R equals 0.05 or 0.10 or 0.15. N equals 2 or 10 or 30 or 60. And J is 0.05, 0.10, 0.15. There are 36 possible combinations here. The smallest one is 0.05 and 2. Now, I'm the first person to tell you, this sucks. But let's do this in gross behavior. Macaulay duration is the sum of T times the coupon payment, 1 plus J to the minus T. t equals 1 to 2. There are only two of them. Oh, I need to put in the rest of the numbers. Hang on a second. And then the actual redemption is the face value, 1 plus j to the minus n, divided by all of my coupons brought forward, FR 1 plus j to the minus t, and the redemption value brought forward. If I really want to do this right, I need the actual face value. So let's F equals 100, R equals 0.05, J equals 0.05, and N equals 2. So I get the sum from 1 to 2 of T times 100 times 0.05 times 1.05 to the negative T plus 2 times 100 times 1.05 to the negative 2 over the sum t equals 1 to 2, 100.05, 1.05 to the negative t plus 100, 1.05 to the negative 2. Bleh. All right, hang on a second. This is a lot fewer numbers than I actually need. To do here, there are only two things in each of those sums. So when t is 1, I get 1 times 100 times 0.05 times 1.05 to the minus 1. When it's 2, 2 times 100 times 0.05 times 1.05 to the negative 2. So these are the two coupon payments, and this is the redemption value. Down here, I just take away the 1 and the 2 and the 2 that are not in parentheses from the top. Do you see how the numbers on the top and the bottom are the same except for the multiplication by the time factor? Give me a number. So if I work out the number on top, what do I get? Great. That's the weighted spread of all of my payments. I need to know the bottom number now. Wait a second. This bond is bought at par. R and J are the same. I think, but we should check. I think the bottom should be 100. Let's find out. Yay! The textbook only takes this duration value to three decimal places. So the book actually shows 1.952. It is an atrociously large bit of algebra to write this up in a formula that gives me something nice, even something useful in all of this. And I will tell you that I think it's not trivial to get there from here. So here's our disgustingly long, ugly formula, right? There's our numerator. And there's our denominator. And there's the number we just did, 1.952. Yikes. Now, again, what we've really got here in this part of the formula, let's look at this for a minute. This is an increasing annuity, isn't it? This is the sequence of payments, FR, and it's going up by T each year. So that's 1, 2, 3, 4, it's double and triple. So that's an arithmetically proceeding geometric annuity. I know how to do this. There's a formula for that. Let me copy that sucker down again. White balance, please. Thank you. Sorry. That upper left term, this thing right here, F and R never change. The only thing that changes are T and the T on the interest rate. So let's take the F and the R out. We'll leave this alone. And I'll do the same thing in this lower sum, FR, times the sum 1 plus j to the negative t. T equals 1 to n. The term in parentheses in the top row. That's our arithmetically increasing annuity. This thing right here. That's IA. And it's not IA for anything in specific, it's IA with a duration of n and an interest rate of j. So that's IA n angle j. We have a formula for that. Grab the formula sheet out of the textbook or off of our Canvas page. Find me the formula for IA.
Do with minus n b to the n over
Over the rate. Okay, hang on. This is also a formula. With the annuity due, I do 1 minus 1 plus j to the negative n, that's our v to the n, over j over 1 plus j, that's the discount rate d in the text, or I could put the 1 plus j on the outside. I left it on the inside for the moment. Then I've got an n and a v to the n, and then that whole thing is over j. All right, wait a second. Let's simplify this. We'll put the 1 plus j on top, and then it'll be 1 minus 1 plus j to the negative n. And then we'll have minus n, 1 plus j to negative n. If I flip this, there's a j on the bottom here. There's also another j on the bottom here. So I make this one over j squared and this one over j. that goes up here. That's supposed to make it easier. Well, it does. I don't have to do a summation anymore. I've done the summation. I do think that's actually easier. So my top now looks like this. Adam, that page that had the annuity formulas on it, or formula sheet from the FM setup, had the annuity due formula on it, right? And that's here. But that starts with 1 and V and goes up to V to the N minus 1, right? Look at this parenthetical term in the denominator. It's going to go V to the first, V to the second, all the way up to V to the N. And in that same section, instead of using the annuity due formula, if I use the ordinary annuity, V plus V, that's also simplifiable. This denominator here, this is also an annuity term. This piece in the parentheses here, that is ANJ. But I know ANJ, and I'm not even going to mess with it. I'm just going to copy it down right here in the bottom. I can now write FR ANJ right off that formula sheet. And there's no summation required. So you can actually turn the Macaulay duration expression into something that has no summations. And that is the formula that appears in the Excel spreadsheet I was just looking at right here. You see, there's the first part over the J squared. Here's the second part over J. And then it's divided by, and there's the ANI term here. Oh, man. This is nauseating. And I mean absolutely gross. But now I can put in all those different combinations based on a face value, in this case, of 1 rather than 100. Because it really doesn't matter what the face value is. The duration is in years. So you'll notice the example we did had a face value of 100. This has a face value of 1, and we still got 1.952. The exact same answer. Duration is independent of face value. As long as the face value is the same f in all the parts of the calculation we're doing here, f itself could really, go back and look at this expression, f itself could really be factored out everywhere and cancels. However, if I know if I know my yield is semi-annual, and I know my coupon rate is semi-annual, so the yield is I per year compounded semi-annually. Sorry, I2 per year, right? No, I% a year. And R is the same thing for the coupon rate. So this becomes an APR. I can do a crap ton of algebra. And I mean 3 pages worth of algebra. This is actually problem number 4 in the textbook. Interestingly enough, in the textbook, where this problem shows up, they made a mistake. They wrote an equal sign here. So if you've got a physical copy of the textbook, that should be a minus sign, not an equal sign. Otherwise, this absolutely does not work. So there's the minus sign correctly read. And because I don't want to subject you to doing all that crap right now, I wrote the solution and it's posted to our Canvas page. But literally, this is a full 2 pages. I'm sure there's some way I could get from this expression to this expression. You'll notice there's no F in here. The face value is all gone. For a flat rate structure, the duration is a fixed value regardless of face. But I will tell you with a completely straight face, I didn't manage to get that algebra. In spite of spending a couple of days on it, I couldn't figure out how to get there from here. So I did it the long way. But I've posted that to our Canvas page. Questions? I redid the Excel table here with that formula. And when I go through and do it again with the formula, I get exactly the same numbers. There's no difference between the numbers I get here and the numbers I get here using this other version of the duration. And that makes me really happy that I got it right. Holy moly, that one's a lot shorter, even if where it comes from is an algebraic nightmare. Wrong button. This button. Okay. Questions? I posted that Excel sheet too. You should go through and play with it a little. Change some of the rates, change some of the numbers of coupons. Let's see what happens as we adjust this. Okay. Remember, we are looking at a function of the interest rate, P of I. I'm going to reach back into the calculus pile. Calc 1, linear approximations. Remember linear approximations? Vaguely. Linear approximation said you could replace a function by its tangent line when you were working really small, right? So if you took a little bitty step from x naught to h, x naught plus h, then you would go up or down by the slope of your tangent line. That's rise over run. So I multiply by the run, I get the change in height, the rise. So what happens if I apply that to P of I? P of I0 plus h. Well, P of I0 plus h is then roughly P of I0 plus h P prime of I0. My duration has something about P prime in it. Which duration thingy has something about P prime in it? And the modified duration is negative P prime over P, right? So if I replace P prime, oh, that makes P prime of I equal to negative D mod I times P of I. I can put that up here. There's a way to figure out what happens when the interest rate changes using the duration, the modified duration in particular. This is beneficial because I know the duration based off of nothing more than the yield and rate numbers in the term. R, J, and N give me everything I need to know about that. And if I can say, oh, well, J might fluctuate a little. If J fluctuates, what happens? I use the duration to figure out what happens. And this is price in terms of the interest rate. So you can tell me how prices are going to change using the duration based on today's prices. This is not the most accurate of things because it's a linear approximation. Linear approximations are by definition notoriously loose. If I have a computer, there's an easier way to do this. Or if I have a small number of cash flows, there's a more accurate way to do this. This particular version, I said it, but I didn't write it down. This is the first order modified approximation. But it is quite literally an approximation, and it's not always the greatest approximation. A more accurate way to do this, especially with a small number of cash flows, might just be a direct calculation with a computer. But we can use what's called the first order Macaulay approximation. Notice that we're now changing from the modified duration to the Macaulay duration. But what we end up with is an exponential expression. P of I0 plus H is P of I0 times 1 plus I0 over 1 plus I0H raised to the Macaulay duration at an interest rate I0. Oh, that is horribly light. I apologize. There we go. Now, actually deriving this requires me to look at our future value of the price change on the interest rate and then do a logarithmic derivative. It's actually a really direct behavior. But what does this mean for me? Let's look at one of the bonds from that example. I'm going to use R equals 0.05. The interest rate I0 will be 0.10, and we'll use N equals 10. So if I'm using, the interest rate is 10%, the coupon rate is 5%, and I'm using 10 coupons, that's R is 0.05, J is 0.1, that's this one right here. $7.661. So that's my duration for this bond. What's the present value of this bond? Right now. Present value of this bond, P of 0.10. Well, that would be the future, sorry, I need a future face value of 100. So let's take that 100 and bring the redemption value back to today. And we'll take all the coupons, 5% of 100 is 5, and we'll bring them back to today as well. Let's run this calculation. What's the current price on this bond? Give me at least 6 decimal places so that we can keep this fairly accurate.
277,164.
So I should pay that today. Now, since this is a straightforward coupon bond, I could just calculate what happens if the interest rate changes. Suppose I goes up by 0.1%. So interest rates go up 0.1%. Rarely do we actually get 1/10. We often get 1/4% or 0.5%, but 0.1%. I'm going to do the approximations. So I is now 0.101, 0.1%, right? But if I use the approximations, scroll back up, here's my modified duration approximation. At 10%, my modified approximation is this. So using this, P of 0.101 should be P of 0.10 times 1 minus H times the modified duration. Wait a minute, H was 0.001 times 7.661 over 1.10. I just factored the PI0 out front. Again, I'm keeping all the decimal places here, 69.277164 times 1 minus 0.001 times 7.661 divided by 1.1. $68.76. 794,680. The interest rate went up. My present value should go down. Higher yield means I earn more over time. My present price is smaller. Now that's the modified approximation. So this is an approximately equal to. Let's actually work out the price at 0.101. What's the actual price at 0.101?
One, 796, 7, 8.
$68.796878 minus 68.794680 divided by the actual price, 68.796878. 0.000003. That's 3/10,000ths of a percent. That's a tiny relative error. But this was the modified approximation. It was a straight line approximation. And straight line approximations are quote unquote easy. I could just as easily use the Macaulay approximation with the exponential term in it and get a similar result. And then I would have had to do this division by 1.1 here. But a straight line approximation is always easier than an exponential approximation. It's just an easier calculation. Since this was a single bond, the actual calculation itself was fairly easy. Oh, I know the exact change. But for a first order approximation, that's pretty damn good. Questions? What happens when instead of looking at a single bond or even a coupon bond, whether it's zero coupon or not, what if I look at a whole portfolio? A whole portfolio will have a series of different cash flows. So I've got lots of financial instruments. I've got zero coupon bonds. I've got coupon bonds. I've got single payment return investments. I've got money coming in. I've got money going out. I can think of each one of them as a series of annual behaviors. So I'm thinking about a 10-year occurrence. Every one of these will be considered as a 10-year series. I don't know how many of them I have, so that's M. So let's suppose that 1 less than or equal to K less than or equal to M. For series K, I have payments at year 1, 2, all the way up to N. So it'll be C1, C2, all the way up to Cn. And I'll put a little superscript K on this just so I know it goes with series K. In addition, I'm going to assume I have a flat rate structure. All the interest rates are I for the whole time. The present value of this cash flow series is some number. Let's call it XK. I have a form. I can do that right now. XK is C1K 1 plus I to the minus 1. That's the present value of the first payment. Plus C2K 1 plus I to the negative 2, all the way up to CNK 1 plus I to the negative N. That's the present value of a series of cash flows. Some of those are negative, some of those are positive. That's okay. According to this cash flow, it's got a duration. The duration, let's use the Macaulay duration, for series K at the rate I. I can calculate that. I'll even use the version we used with the modified duration. Since I want the Macaulay duration, I'll multiply by 1 plus I. The minus sign is there to account for the fact that in the modified duration, there's a minus sign as well. So this basically says I'm thinking of the duration times the cash flow, xk, as being related to the derivative, a differential equation. But this is for series K. I can add them all up. Since I'm just adding, and derivatives are, when you take the derivative sum, you get the sum of the derivatives. I know that the derivative of x with respect to I is the sum of the derivatives of each of the pieces then I can figure out the total duration. And that turns out to be linear. The Macaulay duration is simply based on being able to take the Macaulay duration of each piece. This is again a weighted average. There's that formula sheet I set aside. We think of this as each individual piece. Then my Macaulay duration is really the sum of the duration times the piece over the sum of the pieces. This is another weighted average. I like thinking of this as a weighted average because that gives me a lot more variability here. Here's a portfolio consisting of 4 pieces. It is a 2-year bond with a face value of $100,000, a coupon rate of 0.05, and a flat yield of 10%. And I'm going to make these annual bonds rather than semi-annual. So these are just once a year. Part 2 is a 10-year bond with a face value of $80,000 with a coupon rate of 10%. And again, our same yield. Then we have a 30-year bond with a face value of $120,000. Hey, maybe that's somebody's mortgage. With a coupon rate of 5% and the same yield. And then, for some god-awful reason, I have a 60-year bond with a face value of $75,000. But the reason we bought it is because it's giving a coupon rate of 15%. That's a really, really, really high coupon rate. Hey, wait a second. Rates are all 5, 10, or 15. Yield is all 10. Yes? These are the numbers I did on that previous example spreadsheet. Let me go back and get that spreadsheet. It is still here. Good. Here's the spreadsheet. I'm using a yield of 10%. I want numbers from here. So the first bond was 2 years with a rate of 5%. Duration for 2 years at a rate of 5% is 1.950. So I'm going to go back to the paper and write the 1.950 there. The second one was 10 years at a rate of 10%. What's the duration on that? $6.759. 30 years at 5%. $11.434. 60 years at 15%. Okay. So that's where those numbers on the left came from. Just so you know, I didn't pull them out of my ass. In order for me to know the duration for the whole portfolio, to say, hey, is this a long investment or a short investment? I need the value today of each of these 4 bonds. I need the present value of each bond. Those are our values xk. So I need x1, x2, x3, x4. X1, bond number 1 is a 2-year bond with a face value of 100,000. I'm just going to do everything in thousands. So I'm going to say, oh, the face value is 100. Bring that back 2 years. The coupons are 5. Bring that back. Wait a minute. That's our A. A 2.10. Bring that back 2 years. Again, I need a number. $91.3223. I'm about to hit the clock wall. Do the next 3 bonds. Here's the cheat. What should happen in the second bond? Because R and J are equal, that should be at par. Let's check. But give me the next 3 bonds. We'll pick this up on Tuesday. Hey, we'll see you then. I hope you have a wonderful weekend.